right, so the quick summary is Kiwi. I've come over to Victoria. I've spent 6 years in the Victorian high country exploring for lithium, copper and gold. A lot of effort into the lithium project, which is part of what we'll be talking about tonight, and amongst looking for copper gold porphyry systems and orogenic gold. About a year ago, I jumped ship, came up here to join the GSQ, and I've been here since. During that time, I've stumbled across the Canon Creek lithium project, and yeah, sort of putting my little twist of flavour on that. And there's been some pretty new and interesting breakthroughs in the last couple of weeks and days. So it's all come together and come to a head in the last couple of days. So it's very timely. Cool.
I'm just going to stop here and start the share again.
So while he gets that up, I just want to sort of say thank you to everyone who's here and online for taking the time out to come and listen, come and introduce yourselves. I'll be around after the talk if you want to say hi, if you've got questions as well, but don't come up later. Very happy to talk about this and very passionate to share what we're working on. All right, so we've got two lithium cesium tantalum pegmatite systems here. On the face of it, quite disparate systems. You know, one's located in sort of northeast central Queensland, and the other one's down in the Victorian high country. Temporally, they're quite well separated as well. You know, there's literally 1 billion years in between these two systems. So when I first put this talk together and put the abstract in, I actually thought they might have had more in common on the face of it than they actually do. But this has actually turned into a great exercise in re-evaluating what I know, what I think I know, and what I don't know. So it's been a good little learning exercise for me to cover a few things as well. So in terms of where they're located, the Canon Creek project is located near Georgetown, up in northeast central Queensland here. And then literally just over 2,000 kilometres to the south in northeast Victoria, you have the Durchap Range project. So that sort of covers the where, and the why do we care factor is actually what's contained within them. So as described in the name, LCTs, or lithium cesium tantalum pegmatites, they contain lithium, but they also contain a suite of other elements which may be rare or critical or potentially useful. So although those three elements make up the headline, don't ignore them for other reasons. The other reason why we care is that hard rock lithium, or lithium pegmatites, provide just over half of the world's lithium supply. And a big share of that actually comes from Greenbushes in Western Australia. Or actually from Western Australia, with Greenbushes being the largest producing mine. So a bit of a talk outline. I'll quickly cover some exploration methods. Some will be familiar, some may not be. I'll give a bit of an overview as to what we've done and the data we have on the Durchap dike swarm, and then move into the Buchanan Creek pegmatite system, and then sort of boil it together into a bit of a summary as to what aspects they share, what differ, and how that can inform models of their emplacement. The photo in the background there is a dike called Boone's Dike, and that rock face I'm standing on is pretty much pure petalite. So it's petalite's a lithium aluminosilicate, and it runs at about 4% lithium oxide. Chip samples there range from about 1.5% to 4%, and it represents the core zone of one of these dikes, so it's monocrystalline, if you like. All right, so in terms of exploration methods, they don't always just stick out in your face like this. They're not beside a road, and so sometimes you've got to be a bit creative. And even when they do stick out like this, they may be absolutely mineralogically dead, like this one. First port of call, like with many projects, is looking at the historic mapping and seeing what data has been done before, or has been collected before, what's available. And in this case, particularly with the Durchap dike swarm, the historic mapping was really informative. So there's a lot of historic tin mining around the turn of the century, and as such, the early GSB, Victorian Geological Survey, went out and did a lot of mapping in the area. And this mapping is incredibly detailed. So these dikes, when you geo-reference it, and your GIS platform is almost spot on, like tens of metres out. So it's really remarkable as to how useful that mapping was. I got a little bit carried away with how extensive the dikes were, but the locations were pretty good. And when you compare that to some of the later mapping, where it's a little bit sort of more schematic and maybe less useful, it really is remarkable how we sort of went backwards before we went forwards again. That said, there is some fantastic mapping that was done by BHP and a guy called Brian Cuffley in the mid-80s. And again, that was tin focused before the tin crash in the late 80s. And so we were able to jump on board that data and start looking at those old tin pegmatites, which are now prospective for lithium. Likewise, up in Queensland, we get sheets like this, where we get stream sediments. So this is a stream sediment map for tungsten, tantalum and niobium around the Forsyth area, so right adjacent to Buchanan Creek. And even at this scale, you can sort of see there's a couple of clusters jumping out with some tin in here and tantalum up in the northwest corner. So really good first port of call. This map was put out in the 1970s, so it's, again, jumping back to old data to see what can inform your exploration. All right, Durchap range, we thought we'd treat it, well, having a gold background, we went straight to soils. That had some limited utility. So we collected the soils from a B horizon, sieved, dried them, analysed them by portable XRF. We identified a suite of pathfinders which were actually useful in diagnosing where pegmatites are and aren't. And so these pathfinders are things like phosphorus, cesium, potassium, rubidium, tantalum and niobium, all detectable by portable XRF. The difficulty there is actually how they relate to the pegmatites. So a couple of cases here, Wilson's dikes, the red lines represent pegmatite outcrop. And so you see we get a couple of bumps on, say, potassium, rubidium, some dubious sort of bumps on niobium, some very scattered cesium data, and then tantalum's all over the show. And that sort of demonstrates the story of what we've got here. Sometimes these pathfinders work in soils, sometimes they don't, and it's to do with the element's mobility. It's to do with dispersion of source material. So these pegmatites erode and they shed laterally. We get hydromorphic dispersion. And so really, we ended up abandoning the soils because we had a prospective area that was about 60 square kilometres, and the soils weren't really prescriptive as to whether there was lithium present or not. Now jumping up to Buchanan Creek, another great data set here. So this has been provided by Strategic Metals. This area is covered by sheet wash, so several metres of disturbed and transported sediment, so soils aren't really going to work for you. So instead we've used termite mounds. So termites burrowing several metres into the soil saves you from having to auger through this rocky, terrible soil. But again, we see similar sort of issues. So we see this dispersion in both lithium and cesium, the mobile elements. So we've got a little gully in here, and we see there's a sort of a dispersion of lithium and cesium, these mobile elements, into that gully. Tantalum's a little bit more resistive and sort of stays close to where it's originated. And so maybe a bit more prescriptive for where a pegmatite is, but again, having tantalum doesn't mean you've got lithium. So it's limited utility. Stream sediments. This is absolutely fantastic. So again, this is data sourced from Strategic Metals. There's about 1,200 stream sediment samples here. So these are stream sediment concentrates, fantastic data set, and they've really gone whole hog on this thing. So first thing I want to point out is the lithium data. Again, limited utility. So you'll see that the lithium values, even at their highest, are several orders of magnitude lower than what we're seeing in rock chip data shown in these orange circles. So the rock chips, as a bit of a spoiler, are already giving part of the game away as to where we should be. But I'd actually argue, looking at the data, that perhaps there's some prospective ground out to the southwest here as well. Likewise, to take the tantalum example, tantalum's got a great spread. A couple of other hotspots poking up, both to the northwest and southwest. So I would say there's a fair bit of ground to cover for the guys at SMA. But yeah, nice little case study here. So that red circle there is actually a dike that I'm going to go into much more detail later on. So some exceptional lithium values in the surface, and in fact there's amblygonite, this photo here, a lithium phosphate mineral that assays at 11% lithium, sitting in the creek bed itself, and yet 35 metres down the creek, the stream sediment sample comes back at 50 ppm lithium. So again, another little hurdle to overcome. It's not just as easy as going through and doing your basic groundwork like you would with another system. All right, Durchap range. I know I'm bouncing around the place, but it's sort of pulling together methods and accumulation of data. But here in the Durchap range, we literally drove ourselves in circles trying to find these pegmatites. So the great thing about pegmatites is they're resistant to erosion. They tend to protrude above the surrounding metasediments, and so they stick out through the bush, basically. So I had a great time for a couple of years. We would hop in a helicopter, fly around for a couple of days, pick out a couple of pegmatite crops, and then spend the next 2 weeks sort of bush bashing to get to them. That was great work, loved it, but it was very expensive. And so over the course of about 8 sessions, we identified 300 dikes, and that's spanning about an 80 kilometre by 40 kilometre area. Again, we had to do quite tight passes to get them. The vegetation cover is incredibly thick. I think some of the photos I showed earlier sort of allude to how thick the vegetation is there. So you pretty much have to be directly overhead to spot them. And that's part of the reason why drones are of limited utility, partly because of the large area, but also just the man hours and reviewing them in high detail. And then we lucked onto LiDAR. So for about the same cost as what we put into the heli work, we accumulated a data set across 110 square kilometres, and don't quote me, but I think the ballpark figure was around 70 or 80 grand. There's then a bit of post-processing to go with that. But from that, within a matter of days, we had 220 targets, and we'd also identified a series of historic workings, so around 260 historic workings. And so for anyone who hasn't come across LiDAR yet, it's a little bit more prevalent now, but basically it's like sonar. You send a laser pulse out, you measure the first and last returns and a series of returns in between, and from that you get a point cloud. Within that point cloud, that's comprised of everything the LiDAR beam hits. And so these LiDAR sensors throw out several million points in a second. And you get everything from the treetops to the ground, and sometimes the subsurface as well, where you get mine shafts and things like that. And from that, we can then, principally for our work, we're interested in ground returns, which we can then turn into a digital terrain model. And that looks like this. So this is the area we served across the Durchap range. So you can sort of see, while it's not really accessible for a lot of traditional exploration methods, the highest point here is about 1,200 metres. The valleys are sitting at about 300, 350 metres. We get half a metre to a metre of snow in the winter. It's, hard country to work in. But what's really apparent, even at this scale, is that some of these features are already standing out. So these dikes here, this one here is a great example. We'd driven that road a number of times and didn't know there's a pegmatite there. This pegmatite's 350 metres long and 50 metres wide, and it's only about 100 metres off the road. Likewise, this one we had spotted from the helicopter, but you can actually start picking up little occurrences of it in the southern valleys. So to give you an idea of what it looks like from the air, that's about all you see. So this is a 20 metre high face sitting in a stream gully, and the lateral extensions are basically invisible. So I mentioned workings before. This was a nice little sort of Easter egg within it, I suppose, is that some of these ground returns actually peak below the surface. So where you hit a shaft, you get a return from down the shaft, and you can start mapping mine workings really effectively. So in this case, this was some gold workings out to the west of the project, but it really demonstrates sort of what this point cloud is consisted of. So when you start breaking down the data, there's a huge amount you can do with it. We're able to use the vegetation coverage to look at old forest tracks, to make a case for where or where haven't been affected by fires, incidental things that affect your exploration programs. All right, once you've found it, it's still hard. So the mineralogy is all over the show. So in particular, the lithium-bearing minerals tend to break down over time, and fairly rapidly over time as well, till they end up looking like fairly amorphous, ugly-looking feldspars. So this up here is what I'd say is a better preserved example of a petalite crystal, and that's defined by that really strong cleavage within it. However, it's very easy to see microcline in a field that looks exactly the same. This here is a face of pure petalite. That was just a very nice, happy thing to find. Spodumene, so that ugly brown little crystal there, closer up image of it here. How would you diagnose that in a field? Some better examples. So this is actually from the Buchanan Creek prospect. Really easy to diagnose. You put a UV light over it and it glows. It's pretty straightforward. And there's an example of this here. So this is some drill core from Durchap range, HQ core, invisible light. It looks like a mixture of quartz and albite. Stick it under UV and the spodumene fluoresces beautifully. As a little side note here, there's a good case to be made for the nugget effect here, where you get 20 centimetres of spodumene, which may grade somewhere between 4 and 8%. what's that do to your grade? Is it real? Is it representative? Hard to see. And the other thing is just going back to some real basics and doing a flame test. So lithium burns red, and quick and easy way to tell if you're really unsure. Just bouncing around on the UV example, and I've also brought a UV light and a couple of examples of spodumene in up the front if you're interested after the talk. But here's a couple of core trays from a Durchap project under natural light, under mixed UV from a cheap sort of UV lamp, where you're seeing both the spodumene and the microcline fluorescing. And when you actually break down those spectra, in a shortwave spectrum you get microcline fluorescing, and under long-wave UV you get spodumene fluorescing. Or else in this case up here you've got nicely cleaved crystals, which are again fairly diagnostic. At the GSQ we're lucky to have a high logger. So last week Dan, our high logger technician, actually ran the SMA cores through it. And so recently I identified spodumene in one of the holes, and that stands out beautifully in the spectra. So here's another example from our handheld spectrometer. A perfect match for spodumene. Really, really fantastic. So what you're looking at here is we're looking at several metres of amphibolite, both in the top of hole and the bottom of hole. And then we're looking at a pegmatite, which is largely comprised of quartz, with a core zone containing about 4 metres of spodumene. Well, spodumene and quartz, I should say. Almost no lithium mica is present at all in this hole. Oh, and a little animation. So the beauty of this is you get a lot of data really quickly. So it's a really good first pass assessment of things. And you also get really nice core tray photos, which I've seen some really ugly ones in my time. These are all colour corrected and really nice to work with. We also have a few other toys to play with at the GSQ. So we've got access to TEMA through a collaboration with QUT. We've got an in-house micro XRF unit, and we've also been using LIBS mostly through an external provider in Perth. And this opens up a whole new world of sort of paragenesis on the small scale. So it's been really, really fantastic to do a deep dive into better understanding these things, rather than just thinking about grade and scale, but actually think about how they're in place and how we can understand them. All right, into the face-off. So we've got the Durchap range, which I'll be leading with, and then followed by our work on the Buchanan Creek project. So in many regards, the Durchap range work is a lot more advanced. I'm only just getting my teeth into Buchanan Creek, but yeah, there's still some cool stuff coming out. So already we see the terrain and the climate are already quite different. So the Durchap range is steep, thickly vegetated. It's a little bit closer to town. It's only an hour's drive from Albury, whereas Buchanan Creek, it's a lot drier, but a bit more open and a little bit more accessible. All right, so Durchap Range project, it's operated by Dart Mining. They've got an earn-in agreement with SQM, one of the largest lithium producers. It's located in northeast Victoria, and the dikes are in place at about 420, and that's based on pretty much a single monzonite uranium lead date. The host rocks are the homometamorphic group, so metasediments, and they're in the green schist facies. Mineralisation is almost primarily spodumene and pedalite, and we've got a range of exploration data to work with. We've got a very similar range of data from the Buchanan Creek project, give or take a couple of methods. And the Canon Creek project is run by Strategic Metals Australia. It's located in northeast central Queensland. That age up there, thanks to Renji, is absolute bollocks, and we'll talk a little bit about that later on. He got me a slide about, I don't know, 10 or 15 minutes ago. The dikes are hosted in the Lane Creek formation, so it's either late Paleoproterozoic or early Mesoproterozoic. And the primary lithium mineralisation is lepidolite and amblygonite. All right, so looking at the Durchap dikes form, so we're down here in Victoria. We're located up in the northeast in the high country, and like I said, we're about 60 kilometres south of Albury-Wodonga, and the dikes form spans an area of about 80 to 100 kilometres heading down to Glen Wells in the south. A range of data available, so most of my time at Dart was actually in the bush chasing rocks. So we collected a bit over 1,000 samples across around 800 individual dikes. So again, these dikes span a very large area, roughly about 85 by 40 kilometres. We attempted soil surveys. We sort of gave up on those after a couple of weeks when we realised that it wasn't particularly diagnostic for lithium. And then we had a couple of cracks at drilling it as well. So 2019, we put an RC rig in and drilled 2 of the more accessible dikes. And then with SQM's help, we came back in last year and we put 12 holes into 5 different dikes to test their grade and depth and structure. All right, so out of the rock chip data, we're able to pull out some really neat geochemical trends. So this is only part of a suite, and this is all published data. This is published in AIGs last year. Effectively, we can see some spatial trends developing out of the data. So we've got this broad data set. We've got very low beryllium at the extremes of the project and on the outer edges, but we've got a hotspot in the middle. And the same can be said for lithium, except that hotspot's a little bit tighter. Same for cesium, and likewise tantalum. So tantalum and tin tend to range a little bit further than cesium, and there is reasons for that, which we'll get into. And from there, we actually took the 75 highest grading samples, so basically anything over 0.1% lithium, and we ran it for XRD, and that demonstrated that the bulk of this project, the bulk of lithium mineralisation, was hosted in spodumene. Seems like there's a little bit of zonation to the mineralisation as well, so the outer margins are characterised by petalite, and with a little bit of amblygonite occurring towards the eastern edge. Cookite is a hydrothermal alteration mineral that comes from the alteration principally of spodumene, and that tends to occur more towards the west of the project, where we have these later overprinting sulfide gold mineralisation. So different ways to dice up data. So this is looking at enrichments relative to crustal abundance. So again, we get a fairly distinct trend here. And we'll talk about it later, but we get the exact same pattern out of the Canon Creek pegmatite dikes. And so that's more to do with the processes of formation and emplacement rather than mineralisation and what minerals are hosting the actual elements. And this differs. It's almost the inverse case of the spatial trend we see. And again, that's to do with how incompatible different elements are, what mineral phases they're being incorporated into, and also what fluids are actually fluxing the elements at that time. So in this case, I would argue that it's probably a phosphate-rich fluid with a beryllium component fluxing everything. And for the sake of argument, I've also just cut out the upper quartile so the upper 25% of highest grading lithium samples, and we still see that same enrichment trend. So beryllium and cesium swap places, but the pattern stays the same. It's slightly skewed a little. And a reason for that sort of little exercise is, what if you're high grading your data, in the case of going through and grabbing grab samples rather than chip samples, what sort of things are we going to see in the data? We're still going to see those same enrichment trends. So it's good, it's useful. All right, placing some of this in context. So again, this is some of the diamond drilling data we did last year. And so we see 3 holes here into what we call the Eagle dike. It's the largest spodumene-bearing dike in the Durchap system. We had 3 RC holes map out several dikes at depth back in 2019, and they all graded very low. So the highest hit was about 0.3% lithium oxide, whereas surface was grading about 1.3% over 10 metres at surface. Similar results from the diamond drilling, but the upside from diamond is we actually get structural data as well and a little bit more context. So from this, we're able to see that there's actually, rather than a single large dike, as you'd expect from the outcrop expression, we've got 3 much more smaller, discrete dikes that are actually occurring as pods at depth. They also plunge towards the northeast at about 35 to 45 degrees. And we also see several periods of reactivation on these structures. So they've had a pretty hard life, and they've also acted as a brittle host to some late-stage sulfides. So if I jump to the next slide, we see, one of these holes, we actually get 0.5 metre at nearly 2 ounces of silver and 30% zinc. But the real name of the game here is actually the pegmatite itself. So again, thinking about pathfinders and how they're reacting, how they're responding, thinking about the elements and their mobility and how they're emplaced. Beryllium does a really good job of identifying the dike. So the pegmatite here is shown in blue, the metasediments are in green-grey. Whereas cesium, on the other hand, fairly low within the pegmatite, but highly enriched within the wall rock. And the same can be said for lithium. You could argue there's more lithium in a wall rock than there is in a dike. Same story for rubidium. And so the common feature of them is they're all mobile elements. They're all highly labile, so there's a little bit of a pattern emerging here. On the other hand, things like niobium, tantalum, and beryllium are all pretty happy where they are. They stay with the pegmatite. They don't get remobilised. So to take another case, this is Ferguson's, another couple of holes in there. So again, it's a single dike. It's fairly narrow, fairly continuous. We still see that same reactivation on the contacts. We also see a little bit of sericide alteration on the contacts. We see some solution banding in some weird phosphate minerals where we get these blue phosphates forming within the pegmatites. And we also have nice coarse spodumene, as you saw earlier. Downhole, sampling resolution is a bit coarser, but we're seeing that same sort of trend where beryllium and tantalum are fairly happy in the dike, and things like cesium, lithium, lesser extent phosphorus, and also rubidium are moving out into the wall rock. And that brings us into alteration. So these things haven't just been in place and then just sat dormant. They've actually gone through a couple of orogenies, as well as some sort of metasomatic fluid flow, which has led to later gold sulfide mineralisation. So as mentioned, we've got some strong sericide alteration in places. We get eucryptite as a low temperature, low pressure lithium mineral replacing the rims of some of these spodumene crystals. Despite having really highly lithium, rubidium, cesium values in a wall rock, there's no visible alteration at all. And again, we see some secondary phosphates. So we're seeing some dissolution, reprecipitation occurring within these rocks. Further to that, I mentioned a couple of orogenic events. So we can actually see that much of the system was actually originally pedalite. And so you take pedalite, you run it through a metamorphic pathway, and you end up with basically spodumene plus quartz, pedalite leading to spodumene plus quartz. And we see that in our thin sections where you get these really wormy little textures where the quartz is actually, this pedalite's gone into solution, precipitated spodumene plus quartz. Really neat, really diagnostic, and using that we can actually find a metamorphic pathway for this based on the composition of both the metasedimentary facies, but also the pegmatites themselves. And subsequent to all of this, it's also been overprinted by Devonian orogenic gold mineralisation. Mapping of the dikes, so something we did when we collected all our field data was we actually mapped an outline of every dike. We measured any contacts we saw, any foliation, as well as any metasedimentary outcrops we came across. And it came up with a really cool story. So the dikes are remarkably consistent in their orientation, which sort of suggests they're entering a sort of structurally controlled domain. They run parallel to the sedimentary contacts and parallel to subparallel with the regional bedding trends. So the major governing control on the regional bedding is the Benambran orogeny, which is sort of Ordovician. That orogeny formed a number of really steeply dipping isoclinal folds and punctuated by a lot of shears in the Durchap range region, which is why these dikes have exploited those structures. These have subsequently been overprinted by these early Devonian structures, which are 30 degrees offset, quite distinct, and actually extend out into the country rock. So they're very narrow, very discrete structures, and don't seem to host the pegmatites. Only one sample for microanalysis from this, and it was completely by accident. So one of these outcrops is full of these beautiful big cassitterites, really lovely stuff, which we were hoping to use as a standard for uranium lead dating. So cassitterite uranium lead is a fairly recent technique, and we're still trying to find standards for it. This case, however, that went out the window when we found all the zonation within these cassitterites. So really interestingly, it's got lithium inclusions, it's got zone tin, not surprising, it's cassitterite, but it's also got this beautiful niobium, beryllium, as well as tantalum zonation within it. And these are hosted in grisonous veins that actually cross-cut the pegmatite dikes. So these are already late structures. These muscovite-dominated tin grisons, and already we're seeing remobilisation of different elements just encapsulated within those cassiterite grains. So a nice little summary to sort of say that, yeah, things are moving. Elements aren't really staying put within these pegmatites. All right, from there into Buchanan Creek. So this is a nice little aerial shot of a region. For scale, there's a couple of land cruisers in the corner down there, and this is one of these pegmatites outcropping in the landscape here. So again, this is a large pegmatite dike, probably on the order of 100 metres across, 20 metres wide, and hosted within the Lane Creek Formation. And in the background on the skyline, you've got some of the Kennedy Province Kennedy intrusives. So in terms of where we are in the world, Buchanan Creek is located just north of Charters Towers, just south of Georgetown, up in northeast Queensland. That gives you a sense of the neighbourhood. And then we've got this lovely data set that SMA have provided, consisting of about 500 samples, with another 30 odd samples collected by myself and a few others. And this is how they pan out. So I won't show you everything, but for the headliners, lithium, cesium and tantalum, again we see discrete trends. So Buchanan Creek, that's where all the lithium action is, and the rest of the area is effectively dead. Cesium, a little bit of action up around the northwest, and same with tantalum. Tantalum's a little bit more widespread. Similar story for tin, niobium, rubidium. Tin tends to follow tantalum. Niobium's sort of hit and miss, and rubidium also tends to follow. Now, I mentioned before that this has the same enrichment trend relative to the average crustal abundance as the Durchap range, and there it is. So again, great data set, really highly enriched in a lot of these elements, but then that's a matter of the mineralogy at this point. So actually what's controlling the enrichment within the dikes. So in terms of what this actually looks like, most of the mineralisation at Buchanan Creek is hosted within lepidolite. So we've got our nice little sample of lepidolite up here. We can see it's got a lot of lithium distributed throughout it. So this is an example of a LIBS map. So that's laser-induced breakdown spectroscopy, which gives us a really good overview of light elements. And in that, we can actually see that lithium is hosted here in the micas, but also within these tourmalines. So it's really well demonstrated by the boron here, as well as potassium, cesium and rubidium also being hosted within the micas. We also have the odd little bit of beryl, the odd little bit of coulimite, which is a niobium mineral, as well as the specks of cassiterite plus tantalite. So we can see there's a few things going on here. And if we actually look at some drilling data, there's a few more things going on. So both these holes are in pegmatite free, which I'll talk about on the next slide. But we see some clear zonation within the pegmatite. So we have a core zone, which is comprised of lepidolite, an outer margin, which is lepidolite plus quartz, or lepidolite, quartz and albite. And then we have our wall rock. And again, like the Durchap range, although perhaps to a lesser extent, we're seeing this enrichment of the wall rock. And unfortunately, it's hidden up here, but I promise you it's also present in rubidium, lithium, cesium, and phosphorus. Similarly, tantalum staying put, it's restricted to the pegmatite, doesn't make its way into the wall rock, same with tin. Hole 10, which is my really happy spodumene hole, that shows similar features. So again, wall rock really strongly enriched in cesium. Lithium is slightly enriched in the wall rock, and it's just because the scale is blowing out here to nearly 3% lithium, but you're not really seeing the wall rock enrichment. And so on and so forth. So I mentioned before that the micas are really rich in cesium, potassium and rubidium. Little clue here is that we're not seeing any rubidium at all, and we're hardly seeing any cesium within the actual pegmatite itself as well. And yet we've got such strong lithium. Also incidentally, we've got a little bit of silver within this dike as well. So we've got a meter running at 1 gram silver, and Lisa Kearney, who runs the teamer over at QUT, actually asked me the other day what native silver was doing in one of the pegmatite samples. Well, that's probably what it's doing. Anyway, on to spodumene. So going through these dikes, we noticed the assays didn't contain rubidium or cesium, and yet we're highly enriched in lithium. And when you actually see the material, it just stands out like the proverbial. Really hard to miss it. You stick it under UV light, and it really stands out. So I've got the sample up here tonight if anyone's interested. You run it through libs, high lithium, high silicon, so it's quartz spodumene, and with a little bit of micas along with fractures. So there's a little bit of polylithianite caught within the fractures here. And all in all, we've got 4 metres running at nearly 1.4% lithium oxide. Another nice example, same hole, just different mineral structure. This is absolutely beautiful mineralisation where you get these nice radiating pencils of spodumene, beautiful textures. Comes up really well in automated mineralogy. So the white showing spodumene, blue showing quartz, and the grey there is showing an epoxy band where I've glued the sample back together to try and increase my area. All right, so this is the dike, and I apologise because there's a lot to take in here. Basically, these square boxes are surface samples. No spodumene visible in any of the surface samples. So you do get amblygonite in places, and that tends to grade really well. So pure amblygonite tends to run at about 11% lithium or around 19% lithium oxide. There's a fair bit of lepidolite. So lepidolite tends to run anywhere from 1 to 4% lithium, lithium oxide I should say. And these are well in that wheelhouse. They're sort of running at around the 3% mark. Also quite highly enriched within tantalum, particularly around this part of the dike where we get a little aphylitic dike which is full of cassiterite and tantalite. Really high cesium, and again that corresponds with where we have the lithium micas. And then as we get down towards the northeastern end, we sort of break into this quartz and amblygonite rich pegmatite. So we go from muscovite at the far end, lepidolite to lepidolite albite quartz into quartz amblygonite. So it's already showing zoning at surface, and it's actually, I should say, the strike length here is 135 metres, and it extends even further out towards the northeast here. So some trenching done by SMA picked it up just on the other side of a creek here, and some rock chip sampling picked it out even further out. This image shows the outcrop in the creek. So by the time you hit the creek, we've got a metre of pure amblygonite, not much else going on there, with metadolerite either side. If we look at some of the costines done by SMA as well, so back up through the lepidolite dominant part of the dike, we see we're getting 18 metres running at about 1.1% lithium oxide. So good numbers, and yeah, up to almost 2% lithium over a 10 metre core zone. When we start looking at the drilling data, so this transect is taken through roughly where that costine is, slightly to the southwest. We actually see, like the Durchap range, the grade drops off at depth. So no idea why this happens, but it seems to be a fairly consistent feature. So hole 9 here, we've got 14.5 metres at 0.4%. Hole 14, we've got 6 metres at 0.3%. And by the time we get down to hole 16 here, we've got 1 metre at 54 ppm. What this does tell you though, is it gives you an idea of the structure. So between this transect and the southwest, and this transect in the northeast, we're actually starting to see this classic horsetail structure, which anyone who's worked in orogenic gold might be familiar with. Nice dilational zone. Not surprising that it's filled a dilational zone, but it tells you something about this thing filling a void that was available to it. So we're obviously extensional, well, maybe a zone of extension within a compressional regime, but also it's telling you that it's dipping to the southeast, plunging to the northeast. So this transect is where we get interesting. So this is below the amblygonite in the creek here. So at the surface, we've got a metre running at about nearly 10% lithium. And then 20 metres below that, we've got nearly 8 metres at 0.7% lithium with a 4 metre zone at 1.4% lithium oxide. And this is spodumene at this depth. And this is an example of that core at depth. Forgot to mention the lepidolite in hole 9 is truly remarkable. So you get these almost UST style textures where you get interlaid bands of albite and lepidolite. So it's almost like USTs where you're going between states of equilibrium for different minerals. You also get brecciated clasts, which have been rimmed by albite and quartz, and then by lepidolite. So some really funky stuff going on. Clearly been reactivated, dissolved, and reprecipitated at some point. So how and why spodumene? Why haven't we recognised it till now? Partly it's about knowing what you're looking for, and that's sort of what that slide about messed up lithium minerals was about at the start. But it's also about what to expect. If you're looking at a lepidolite-dominated project, you're probably not thinking about spodumene. And more to the point, how did it get there? Well, it's almost certainly primary, so probably magmatic, and then it's been altered to amblygonite montebrasite. So there's been plenty of opportunities within these rocks. They're nearly 1.5 billion years old, so they've had a lot of time and a lot of deformation events to overprint them. And there's a pretty well-established pathway for that, where you take spodumene, you soak it in a phosphate-rich fluid, and you end up with montebrasite and amblygonite. Now going back to some of our surface sampling, we can actually pick up some samples which have bits of spodumene, these little lithium-enriched spaces with low rubidium and low silicon, amongst our other elements, sitting within the interstitial spaces of some of these samples. Talking about alteration, there are plenty of indications for subsequent alteration events here, and trying to put them into a cohesive story is a bit hard because there's just so much going on, and it's fairly early days at the moment. Some interesting features we can pull out though. Hole 26, we've got this wall rock contact zone, which is full of these sort of several centimetre scale garnets. These are spessartine, so that's showing high manganese, it's showing interaction with the wall rock, so between the magmatic fluid and the wall rock. And the fact that you've got manganese present means you're probably not going to get lithium, because all lithium-bearing minerals are much more susceptible to taking up manganese than lithium, so they're far more receptive to that. And in support of that, this dike was actually dry. Hole 25, we see late-stage sulfides. So we're seeing these pegmatites acting as a nice brittle host, and they're being overprinted by pyrite, peritite, and a little bit of chalco. And that's shown in these tornado maps here, where we see these nice little blebs of sulfide with these chalcopyrite rims. In addition to that, going through some thin sections, we're seeing a range of deformation features here. So we're seeing multi-phases of lepidolite precipitation. We've got these older, chewed up lepidolite shown up by the high birefringence colours up here, and these happier ones as well, sort of presumably a little bit later. Zinnwaldite, another lithium-bearing mica, has been identified in the project, and these tend to be more in equilibrium with the material. So perhaps they're either later or they haven't been chewed up to the same extent. I've got no reasons why, but that's an interesting observation. And likewise, the albite, the lithium tourmalines, are acting like snowball garnets. So we can see that there's been some strain across these. We can see they've rotated and deformed the matrix. And we can also see they've come out of equilibrium, where they're starting to form these little quartz globules as the tourmaline's starting to go back into solution. All right, and as I was walking here, Renji sent me a message saying, hey, I've got a slide for you. So hot off the press, he took some cassiterite samples from Buchanan Creek up to JCU last week. These were only run on Wednesday or Thursday to get some age data for us. So all we've been working with previously were some argon ages that the GSQ got in 2019. And the reason I said they're garbage is because the profiles are so wonky that it's hard to make heads or tails out of them. At our best guess, we're sort of going, well, maybe they're about 1430 because there's a consistent age between the host granite and one of the dikes. But then the K feldspar tells a completely different story. These two at least give nice cooling profiles despite being different ages, but this one gives a really wonky one. So I think the take-home message out of those profiles is that they're recording subsequent metasomatic fluid flow. However, we have cassiterite. So we're getting some good numbers out of these, and this is more in line with what we'd expect. So these numbers put us more in line with the Forsyth granite, the Forsyth supersuite, which is not surprising. That's a major S-type granite in the region. These things are generally derived from S-type granites, so this is really good to see. The other benefit is that cassiterite tends to precipitate really late stage, so it's providing a sort of a younger-most bracket to the emplacement of these things. Not everything goes to plan, so some of the data is a little bit wonky. It might take a little bit of finessing by Renji's magic hands. But out of 5 samples and 1 duplicate that was sent up, we've got four consistent ages. So there's a good story coming out here, and I'm pretty pleased to get that last minute message. All right, in summary, so I think the best summary is to poke a hole into things. So here's 30H1 having a crack at the Durchap range in some pretty trying conditions. So these guys got snow on a rig, it was in the middle of winter, 1,200 metres, and their water supply was 14 kilometres away. So yeah, some hard times up there. But to summarise, distinctly different ages. Metamorphic grade of the host rock is quite different. So the Durchap range is sitting in green schist facies, whereas Buchanan Creek is sitting a bit hotter within amphibolite facies. The principal style of mineralisation is a bit different, although they share some common elements. Durchap range is principally pedalite and spodumene, with some minor cookite and bligonite and lepidolite, particularly down south. Whereas Buchanan Creek is lepidolite and bligonite dominated, with now, as of a few weeks ago, some spodumene mineralisation. The elemental enrichment trend is 1-for-1. It's the same process that we see here. It's the spatial zonation that differs, and that spatial zonation is related to the mineralogy rather than the actual emplacement process and the enrichment process, which I'll go into in a minute. Both have exomorphic halos, and in both cases it's the labile elements which have just dispersed into the wall rock. And I think there's a really good case for suggesting that this has probably happened post-emplacement, not during emplacement. So there are arguments in the literature for this, but I would say if it was happening during emplacement, you'd also see enrichment in some of the less labile elements. So you'd see things like tin and tantalum soaking into your wall rock if your wall rock is simply acting like a sponge to the original fluid. That's not what we're seeing. We're only seeing the mobile elements move, which suggests that that's probably happened at a later date. All right, dike zonation. In the Durchap range, it's pretty much absent. We looked for it, we were pretty convinced it had to be there, and at best we could sort of pick a weak latitudinal gradient across the width of the dikes where one side might be more enriched than the other, but it was a fairly weak trend. In the Buchanan Creek project, it's a bit more common. So we see this either concentric or latitudinal zonation down the dike, like what was shown in pegmatite 3, where the outer margins are mica rich and the inner margin is quartz to spodumene rich. Both are structurally hosted. The Durchap range, we're pretty confident that occurs within a shear zone. Buchanan Creek, we just don't have the data yet to say. We've certainly got a dilational structure that these things are intruding on, and it's possible that a regional shear exists. There's certainly lineaments within the geological data, but it's going to take a bit more work to pull that out. There's at least 2 overprinting deformation events in the Durchap system, and that includes sulfide holstered refractory gold with some lead arsenic mineralisation. And at Buchanan Creek, we see at least 3 events, probably more, and we're seeing some base metal and some silver mineralisation there. And there's plenty of further work for both companies. I've sort of already covered a bit about exomorphic dispersion into the halos of these things. Lithium grade is really variable, and that relates back to that nugget effect, especially when you're dealing with things like spodumene and pedalite, more so than with lepidolite. We have a great understanding of the structural controls on the Durchap range, but we need to work on Buchanan Creek, and that's the plan going forward. And we also see the same pattern of enrichment here, especially in beryllium and cesium, and these are 2 critical elements, both incompatible elements within the melt, which will help explain the model for how these are emplaced. All right, so emplacement of these things, you typically need a marine shale, and that's because it provides a really good source for phosphorus, beryllium, lithium, cesium, niobium. So basically you're taking clays, you're taking micas, and placing them within an S-type melt. And the reason why we want those is we want particularly beryllium, fluorine, phosphorus for fluxes. So this thing is, the emplacement of pegmatites is all dependent on having a good flux. So if we step that over into stage 2 here, the depth of emplacement becomes really important as well. So if we take beryllium as our key example, beryllium in your average marine shale or your average crustal rocks is around between 2 to 6 ppm. So to actually get a melt which is enriched in beryllium isn't actually that easy. It's pretty incompatible with most silicates. So even if you take a single melt, precipitate out most of the aluminosilicates, you'll be left with only a marginally enriched beryllium. So for example, if you take an anatectic melt at 6 ppm beryllium, you fractionate out 75% of the aluminosilicates, you'll be left with a melt fraction in which about 12 ppm beryllium remains. So you then have to fractionate that fraction again. So that leads to this sort of this dual mode model where you have multiple fractionation events. You can't do it for a single fractionation. Likewise, you have to be below the stability zone for cordierite, otherwise cordierite tends to suck up any available beryllium up to weight percent levels, and you end up with these barren pegmatites. So it provides a clear pathway for both systems. Both systems we see up to 800 ppm beryllium, so they're super highly fractionated. We've gone through multiple rounds of fractionation within these apical melt systems. And then they get injected into the environment. So you also need some sort of tectonic control to release that. So it's got to be the right situation, the right melt at the right time, and the right connected fluid pathway. And once you're injecting that into the environment, you've got that final fractionation where your less fractionated pegmatites are either barren or might be cesium and beryllium enriched, whereas your later ones are lithium, tin, tantalum enriched. Anyway, that was a heavy slide. Thanks to everyone who's helped out. There's been a huge amount of contributors, both up here and in Victoria, and couldn't have done it without you all. So thank you very much. And one last plug for the roadshow. It's free to attend, you just got to get yourself there, but it's a day and a half of talks plus a core workshop at the end. I highly recommend going, but yeah. All right, any questions, anyone?
Thank you very much. I'm sure there's a question out there somewhere. There's one.
Yeah, on your last slide there, the vertical extent of that zonation, what would that be?
Yeah, great question. So I heard the alarms going off and started rushing the last couple of slides, so fair enough. It differs between systems, but there's a theoretical maximum of 10 to 12 Ks, and that's what we see in the Durchap range. So we've identified the host pluton, and most dikes are barren to within about 2.5, 4 kilometres out from that host pluton. And we see enrichment in tin and tantalum up to right on about the 10 kilometre mark out from that host pluton. And most of the lithium enrichment occurs about 6 to 8 kilometres out. So there's a really distinct zonation. Buchanan Creek is much more tightly constrained, so we start seeing lithium enrichment in less than a kilometre from a host pluton, or the presumed host pluton, and extending out to maybe a maximum of 5 or 6 kilometres.
Okay, more questions? Another one. I'll just stand here, shall I?
Yeah, just one about your termite mound sampling.
Yeah.
How did you process that? What was the
Yeah, so that data's straight from SMA, but as I understand it, they knocked the top off and sent it to the lab. So it's been run for your standard lab suite through ICP-MS and XRF, depending on the element you're looking at. But yeah, I think Brad Crichton and Graham Willett might be sitting in the online audience, so they might be better placed to answer that.
Another question?
Do you have fluorine data in Victoria? Is fluorine important?
Fluorine is very important, but it's also very expensive. So as an exploration company down in Vic, we didn't worry about it. It would be very nice to have, and it would have made resolving our model. So all the Durchap range stuff is actually published in April last year's issue of Australian Journal of Earth Science. But yeah, I wish I had fluorine data.
So what's the go?
Sorry?
What's the go? Why is the fluorine from the magmatic fluid, or is it from the sedimentary stuff?
Yeah, so fluorine is derived from the magmatic fluid, and it's a really important flux. So fluxes are the key to this whole story. The only reason you can get a pegmatite 10 kilometres out into the host rock is by having a flux that keeps everything in solution at lower temperatures.
I've got a question.
Yeah.
I mean, they're volumetrically small, and put a little bit of cover on it, and if it's a bit hard to do soil sampling or any kind of augering, Is there any geophysical techniques that are coming forward that can help identify them?
Well, not really. So,
That was the answer.
unfortunately, these things at a geophysical level are almost identical to the host rock. So they've got no magnetic signature. They've perhaps got a weak radiometric signature, but nothing that you'd resolve through most radiometric data sets. I've heard some success with deep ground penetrating radar, but again, if you've got country like this where you're dragging over several centimetres of sticks and twigs and crap, you just forget about it. You don't have good ground contact. So yeah, not really.
They're a bit tough. Thank you. Any other questions? No, just check the folks at home. No, all good. I think that's it. So, last moment, thank you, Ben. And hopefully we'll see you all here again next month with a bit of luck. See you all.